want to say a very good afternoon to all of you. You are welcome to the 6th UESD International Virtual Seminar Series. And I welcome you once again. As you already know, this is an innovative idea from the leadership of the University of Environment and Sustainable Development under the headship of Professor Eric Nyako Samson. The purpose of this international virtual seminar series is to bring great minds, top-class research to local universities as part of the learning experience, because we believe that iron sharpeneth iron. It also seeks to inform policy decisions through scientifically justified research findings. Indeed, if this is well received and attended to, we are of the view that it will change the narratives regarding building quality research faculty and making informed policy decisions. To do the presentation for us this afternoon is an excellent scholar, if I'm permitted to describe him like that. This is based on the brief profile about him, and I would like to take a minute or two of your time to really give a background or a profile of the speaker for today. Ladies and gentlemen, it is my pleasure to introduce to you Dr. Edward Bam as the presenter for today's seminar. Dr. Bam is a certified professional chemist, PChem, in Alberta, Canada, with over 10 years of experience in hydrology and water resources research. Currently, he holds a postdoctoral research fellowship at the Department of Atmospheric Sciences, University of Alberta, Canada, where he conducts research on the impact of climate change and land use on Alberta mountain glaciers and the rivers in oil sand mine development. Dr. Bam's work involves a range of activities, including field and laboratory data collection, statistical and numerical modeling, synthesis, and interpretation to develop conceptual models for sustainable natural resource extraction and environmental management. He holds a PhD in environment and sustainability with focus on isotope hydrology and hydrochemistry from the School of Environment and Sustainability and the Global Institute for Water Security, University of Saskatchewan, Canada. He also holds a postgraduate certificate in applied groundwater modeling from the UNESCO IHE Delft Institute for Water Education. He's an alumnus of the University of Ghana as well as the University of Cape Coast, and completed his senior education from the Kwando Senior High School in the Volta region of Ghana. He has over 32 peer-reviewed publications in top quartile journals in the field of hydrology and water resources. And to mention but a few, we have his publications in Water Resources Research, Journal of Hydrology and Applied Geochemistry. He's also a regular peer reviewer for journals such as Journal of Hydrology, Regional Studies, Hydrology and Earth System Sciences, Groundwater, Soil, Water and Air Pollution, Geochemical, among others. His outstanding contributions to the field have earned him several awards, including the Saskatchewan Innovation and Opportunity Award, the International Dean Scholarship Award for his PhD studies, the NFP NOFIC Postgraduate Fellowship Award, and the International Atomic Energy Agency Scientific Fellowship Award. He is a passionate husband, I love that, and a father of 2 lovely children. And he enjoys swimming and fishing at his leisure time. Ladies and gentlemen, Dr. Edward Bam is your speaker for today. Dr. Bam, you have the floor. Thank you very much.
Thank you, sir. And I'm overwhelmed, actually, by the introduction. Thank you for the opportunity to present a little on what we've been working on, particularly in Ghana, and also interact with you about some of the things that you are doing. First off, I want to take the opportunity to thank the Vice Chancellor for underwriting this seminar. I'm very grateful for the opportunity to present. I also want to acknowledge my colleague and friend, Dr. Richard Amfo Otu, who happens to be my mate at the University of Cape Coast, and we have maintained our friendship till today. And he offered me the opportunity to make this presentation as well. I want to further say thank you to my wife and my kids for giving me the opportunity, the time actually to work on this project in Ghana. So on that note, I will talk to you today about water stable isotopes and vulnerability of water resources in subtropical, humid, and semi-arid region of West Africa, specifically is Ghana. I will serve you a 3-part meal this afternoon. You are in Ghana, very early for me here. But basically, I will open you up to the global water security challenges that we face in the 21st century. The second part of my talk will be on how we have studied isotopes in Ghana and what the implications are for water resources as far as climate change is concerned. And the last part will be policy recommendations from the science that we have worked on. So first off, as I said, I'll talk to you about global water security challenges in the 21st century. So basically, globally, water security is becoming a huge challenge. And for this reason, the UN has put in its Sustainable Development Goal, goal number 6, that governments by the year 2030 should be able to provide clean water and sanitation to their population. However, the risk of water security and population increase are contributing to pollution, which is increasing the risk of water security. Now, in addition to the climate variabilities which are associated with precipitation, and when I say precipitation, in this context, I'm talking about rainfall and snow. And in regions in Ghana, for instance, this will refer to rainfall and temperature changes together with land use changes. These are driving this challenge of meeting our water security needs globally. Come to West Africa, the challenge is expected to increase because rainfall projections have shown that over the past 50, 60 years, the amount of rainfall that we receive has either increased or decreased in certain parts of West Africa. And this, in areas where we have heavy rainfall, we are seeing a lot of floods occurring, but also droughts are projected to come along with this extreme condition that we are having in changes in rainfall patterns in West Africa. So what you see here is just a video of what has been happening in Ghana. And here you see heavy rain that is destroying property and washing away farms, interrupting, basic things that we could do in terms of traveling and all of that. And these kind of events are earmarked or projected to increase in the years to come. So basically, let me just say a little bit about the climate change. So climate is changing in that as far as precipitation is concerned, you are going to be having a lot of rainfall at a very short period of time. And then for a long time, you may have no rain. So that's the kind of situation we are going to be facing. So you have drought and floods and all kinds of things. So This will have huge implications for water resources and socio-economic development and our peace. And if you look at the figure that I have here, our water security is threatened, and this will come as a result of the scarcity of water, floods that may come, droughts that may come, and then also pollution that may accompany these changes. And that will impact our energy production. Ghana, we generate energy from hydro, and we are planning nuclear power energy generation as well, which will largely depend on fresh water for cooling. And so that will be impacted. Food security will be impacted, our ecosystems, rivers will dry up, our fishes will die. All kinds of things are going to happen as far as these projections are concerned. Health, the economy will suffer because job losses, we will not be able to produce more to export, rather we'll be importing more. So we'll be depending on foreign aid. And eventually we will have national security problem, because once the economy is difficult, people don't have jobs, there'll be political arrest, there'll be migration, and there'll be conflict over water. So basically this will be the implications as far as the changes that we are seeing in rainfall patterns are concerned. Now we need to have adaptation and mitigation plans, but this must be underpinned by strong scientific evidence or understanding of the system, then we can plan. So currently it's like we are a frog that is in a bowl, and this bowl is on fire, but it's gradual. So we also need to understand what it is and how to get out of this situation. The challenge is that whereas emphasis has been laid on climate change and what will happen as a result of changes in temperature and rainfall on the surface, little has been done to understand what this would mean for groundwater resources, which most of the developing countries we have, and Ghana included, West Africa and several other countries. This phenomena has not been well explored as far as groundwater is concerned. And we anticipate that there will be consequences for water availability and quality as we move through the century. The good news is stable isotopes can help us to identify potential water resources that may be vulnerable or protected from climate change and human actions. Now, in West Africa and in Ghana, we have a lot of isotope measurements that have been done. The challenge is we do not have regional or national synthesis or analysis of these results. That's a minute. And so it's it's difficult for us to actually have a global picture of what is happening and to plan. So you may have local scale studies and all of that, but what is a general picture of what is happening in the country and how can we plan? So that's where isotopes, as I mentioned, have come in. And the goal here is to, first off, knowing that stable isotopes are able to retain distinct hydrological processes and information that are unique to the environment, can we use these stable isotopes that we have as proxies to understand the hydrological changes and climate variability in West Africa, and in this particular case in Ghana? So what we set out to do is to collect all the isotope data that has been analyzed in Ghana, analyze them as in statistically interpret that, and then synthesize the relationship spatially and then temporally, sorry, my voice. Thank you. Synthesize these relationships between rainfall, which is a driver of climate change, the changes in rainfall, which is a driver of climate change, surface water, and then groundwater. And finally, what we want to achieve is to improve our understanding of the regional hydrology and fill the data and then information gap that we currently have. So our study area is Ghana, and Ghana is in West Africa. Basically, these are the areas where the isotope analysis have been done across Ghana. So our data points are coming from here. And you see that we have rivers, we have boreholes, we have rainfall, all of that. Now, Ghana, generally, if you broadly classify it, you have two climates. Semi-arid climate where rainfall basically is less than 1,000 millimeters per year. And then a subtropical or tropical is subtropical, not very tropical, because we're a small area of that is it kind of represent tropical climate. So that's about rainfall in a year about 1,400 millimeters. Now, two major winds blow over Ghana. We have the southwest trade winds and then the northeast trade winds. So one comes to bring us more or less rain, which is the southwest trade winds blows over the sea, and then the northeast trade winds, which mostly when it's period, we have harmattan. So that gives us two basic climates in a country where we have two major seasons, wet and dry, and relative humidity marks about 85% and temperature 35. Now, data collection, we were able to collect about 1,677 records of stable isotopes as oxygen-18 and deuterium. And this came from rain. And then we collected some river and then also groundwater and boreholes. And what you see on it basically is the period that the various data samples that we were able to collect covered. In addition to that, we also look at the climate record, and then we validated this data first off by eliminating all the single isotopes, and then we made sure our DSS values that exceed 20 per mil have been excluded. It's because of the environment and the level of which evaporation can occur. So that's that. Now, in isotope hydrology, just to bring everybody home, we have two benchmarks. If you measure stable isotopes, oxygen-18 and deuterium in water, we have two benchmarks generally that you use to interpret your data. And these benchmarks are just a bivariate plot of oxygen-18 and then deuterium. So you have deuterium and oxygen-18. Your Y is deuterium and then your X is oxygen-18. And that gives you a linear line like you see here. And it gives us a straight line with a linear equation. Now, for those benchmarks, we have what we call meteoric water line. And under the meteoric water line, we have the global meteoric water line. And then we also have the local meteoric water line. And the second benchmark is the precipitation offsets. And the precipitation offsets are what we call, one is deuterium excess, the other one is line condition excess. There are other precipitation offsets, but we'll not discuss that because we did not work on that here. Now, for the global meteoric water line, it's well established in that rainfall samples have been collected all across the globe. Oxygen-18 and deuterium has been measured. And when they plot that line, you have a straight line. And the slope of that straight line is 8. And then the deuterium excess for that line is 10. When it comes to local meteoric water line, these are location dependent. So because we live in different climates and different sources of moisture contributes to rain, that varies. So if you look at this work that has been done by some of our colleagues in the US, you will say that the local meteoric water line varied with various seasons and then also the climate, basically. Now, in Ghana, several people have worked on isotope data, as I mentioned, and they have collected rainfall, and they measured oxygen-18 and deuterium in those rainfall, and then they reported various slopes. So here is a compilation of some of that. And so you see the variation in the slope. So it's up between 6 and say 7.8, basically. So this is what we have. So it varies depending on where they are collecting the data. And in this regional or national analysis, basically we want to be able to integrate all of these to interpret our data. Now come to deuterium excess. just a brief on that. Deuterium excess basically tells you where your moisture that forms the rain is coming from, in very simple terms. Now, the line condition excess tells you how your water sample that you have at that particular time differs or deviates from your local meteoric water line. So if the water sample you are holding or before you right now has undergone evaporation, then that will mean that your line condition excess, if you measure oxygen 18 and deuterium in that water, it will come down. It will be down the slope of your local meteoric water line. Basically, that's it. So it tells you what processes are happening or has occurred after rain has fallen in the area. Results. So basically, this is an overview of how the isotope varies across the country. So the first panel is the rain, the second panel is the river, and the third panel is groundwater, and the fourth panel basically is your deuterium excess. So as you move for rain, when you move from the coast in the south and you head north, your isotopes begins to become more negative. And for rivers, if you move from the south to the north, your isotope becomes more positive, as you can see in the color bar. Now, what is happening here is simple. There's a lot of evaporation happening in the north, and as compared to the south. That's basically why you are seeing that. Now, come to the groundwater. We see that the groundwater, as we move from the south to the north, our isotope composition again decreases, becomes more negative, just like the rainfall. So that's it. But there's something very unique about this data. That is, in the Volta region, we say that if you follow the trend, you want everything to begin to become more and more negative as you move up. That doesn't happen in the Volta region. For a specific reason, that in the Volta region, you have mountains which transpire a lot of moisture into the atmosphere. And you also have the Volta Lake. So this is a very unique area, and that is reflected in isotope composition. We'll talk more about the DSS as we move down. The next thing we did basically is to look at the rainfall isotopes and how they vary by region. As we already saw, they want to see statistically if that is showing us anything. So this plot that you have here is the deuterium vis-a-vis the oxygen 18 for all the rainfall samples that we got from the literature, and then also some of the work that I have been involved in and some other colleagues. Now, if you fit that, we have our slope of to be 7.01, and our DSS is 6.77. Now, what we see is that as we move from the western region, which is in the south, and you head towards the north, you see that there is a decrease generally in the isotope composition. And basically that's what we see there. So rainfall values in the north basically decrease gradually relative to the coast. Now, so this is about the rain. Now we move next to check what is the impact of that on groundwater. And the same way we saw in the general picture, we again see here that the coastal aquifers are more positive, to say, because this is oxygen 18, this is deuterium. What you have here is a site. So the coastal aquifers, matching this, the coastal aquifers are more positive than the inland aquifers. So the same thing that you see in the rain is statistically also measurable as far as the aquifers are concerned. Then the question then is, are these groundwaters that we have in Ghana, are they distinct? Are these aquifers distinct or continuous? We don't know. Some of the isotopes overlaps. Some seems to be different. So, and then also from the region. So what this means is we probably need to do some aquifer mapping and then also some geochemical studies to confirm that. The next thing is, which is the key we want to look at, is the relationship between rainfall, surface water, and groundwater. Now, if you plot the oxygen 18 vis-a-vis the deuterium, this is what appeared for all the samples that we have from Ghana. What we see here is our groundwater and the rivers, and to a very large extent, the wetlands, plot very close to the, or on the local meteoric water line and the global meteoric water line. As we move up, we see the wetlands moving away. This is pure evaporation. So the wetlands are evaporating. Of course, we see the same in the rivers as well. But this gives us some idea about what is happening in the system. First off, because groundwater plots on a local meteoric water line and then a global meteoric water line. What this means is that groundwater is being fed or replenished by rainfall. Two, since we also have surface water plotting very close to the local meteoric water line and then the global meteoric water line, it also means that surface water is also being fed by rainfall runoff, to put it that way. And the same thing applies to wetlands. But as we move, of course, as we move through the period, the seasons, we see the surface waters evaporating, but we will deal with it. So that the issue of groundwater being replenished by rainfall and the groundwater plotting so close or on the meteoric water line brings a lot of questions. One of the questions is, when is recharge occurring? What kind of system do we have? Under what conditions on the surface? What are the mechanisms that are driving this recharge? To mention the last one, because groundwater and surface water also mixes or plots on each other, what it means is that there is a connection also between the surface water and the groundwater that we have. So the key points is rainfall recharges groundwater, surface water and groundwater are also connected. Rainfall recharges or contributes to a stream flow as well. Now I want to dive into the DSS and the precipitation offsets, which has to do with the DSS and then the line condition assess, just to tell where our river or rains may be coming from, what will be the source of moisture that is contributing to this. Now DSS, which is less than +10, is generally considered as a re-evaporated water. So that generally comes from the ocean. So you have the oceans evaporating and then forming clouds and then falling back. And if it's 10, if it's 10, basically what it means is you have a balanced situation in the continental water, not much evaporation is taking place. Now, if it's more than 10 and it's in a positive, then it means that you have groundwater transpiring, rivers evaporating, and they are part of the moisture that is forming clouds and then bringing you rain. And that's exactly what we see. So what we see here is that most of our rainfall are coming from the oceanic sources, and then also some river evaporation and plant transpiration that is contributing moisture. Reason why they are plotting majority of the peaks are here is because of the re-evaporation, because of the kind of climate that we have. Now the line condition excess must be 0 because we are talking about deviation from the local meteoric water. This is a deuterium transform of oxygen 18. So if it's 0, it means that there is no evaporation. If it is negative, it means that there is evaporation. And if it's positive, it means that you might have some moisture cycling around the area. So if you have huge rivers, large rivers, evaporating, then you will have a positive LCSS. So take away from this is that rainfall comes from high humidity, oceanic, and re-evaporated sources in Ghana, which we saw even by the winds that blows over the country. The winds blow from the west coast all over the country from on the ocean. And then groundwater and rainfall peaks also line up. And that is quite interesting here particularly in this case, because earlier on I said that it looks like groundwater is not evaporated before recharge, and that should tell us where the timing of recharge and the systems and all of that are occurring. And that's what we see here. And final one is our rivers and wetlands. You can see they show evaporation signals. So that is quite perfect and good recorded. Yeah, talk about that one. Okay, so because we have data that has been collected seasonally for rainfall and not for groundwater, we were able to look at how the various monthly rains varies. That's the total composition of the monthly rains vary. And then we measure that up with the regional groundwater system that we have. Now, if you see that, you'll see that this is the green here is our groundwater range. That is the average groundwater plus or minus 1 standard deviation. Majority of the rainfalls that we see matching our groundwater basically are the April, May, June, and July. So it means that within the months of April, May, June, and July, we are having a lot of rainfall recharging our aquifers, or those months contribute the most to our aquifers. Now you can look at that in several other details by just looking at the population of the isotopes. So if you take the oxygen 18, look at the population of the various events that we have. This is the national groundwater, the red one. And so the peak tells you that most of the samples fall within that range. So within the range of say 4 and -2, most of our groundwaters fall within that range. And if you match that with the various monthly precipitation that we have, what we see here is that the May peak, the peak of the May rainfall and the peak of the national groundwater, that as you put away, matches May, June, and July. What this means is that recharge in Ghana is seasonal, or in this system is seasonal. And it's also occurring across, across the entire country, basically, that's what it is. And wetland season rainfall, particularly May to July, dominates the recharge. The other question is then, what are the mechanisms of recharge? And you can investigate that by adding some other tools to this. Anyway, let's look at how the seasons are reflected in our rivers and what we can take from that. So if you take your deuterium plot against your oxygen 18, and basically the colors tells us the months of the year where these rivers were, river samples were taken, 2 being February and 6 being June. What we see is that during the wet season, most of the rivers, the select rivers that we have here, Accra, Black Volta, Oti River, Sene, and the White Volta, basically they plot quite close to our local meteoric water line, and then a global meteoric water line as well. And during the dry season, these rivers deviate, or they move away, the isotopes move away from the local meteoric water line and the global meteoric water line, telling us that there is evaporation. Now, looking at this alone gives us some understanding of what these rivers will be able to do and what will happen to them as a result of changes in our rainfall. First thing is, rainfall seems to contribute a lot to these rivers, which means that rainfall runoff. When it rains, the runoff that goes into these rivers constitutes majority of the stream flow in these rivers. The reason being that they plot very close to the local meteoric water line, and then also the global meteoric water line. And the other thing is, when we don't have rain, which is a dry season, we just see these rivers evaporating, So if there is no rain, they are just going to be away. So if we have drought, these rivers may dry out. And if we have heavy, intense rainfall, these rivers may overflow their bounds. So that should be at the back of our minds, that this is what will happen. So if you are doing any construction of bridges and things like that over these kind of rivers, then you should just understand that when there's heavy rain, extreme heavy rain, these rivers may overflow their bounds, and you have to take that into consideration. So as I mentioned, changes in rainfall then will significantly affect these rivers. So flood and drought will do. So the summary of isotope analysis in Ghana, first off, groundwater, surface water, and rain, they show reasonable measurable variations with respect to latitude, altitude, and season. So latitude, I mean, if you move from the coast to the north, and latitude, I mean, when you consider elevation. And then also seasons. So if it is dry season, we see differences in isotopic composition. If it is wet season, we see differences in isotopic composition. That happens mainly for the rain and the rivers. We don't have seasonal measurements of groundwater, so we are not able to tell that. The other one is that groundwater replenishment and surface water flow are directly dependent on rainfall. And groundwater recharge or replenishment is dominated by wet season rainfall. And also, groundwater and surface water are connected. Then that's a broader picture. They are connected. Specific connections must be studied. So this is basically something that you can take and then work or design research around if you are going forward in that regard. And this result suggests our water resources, groundwater and surface water in Ghana, may be vulnerable to rainfall and land use changes, because when land use change, and we know rainfall goes through the soil, right, to recharge groundwater, then changes that are occurring in the land will be reflected in our groundwater. Our policy, the part 3, we talk about some policy recommendations. So I just have 5 key policy suggestions here. First off, we notice that there will be period from the climate change projections and from what we see in the isotopes. It's clear that groundwater is dependent on surface and on the rainfall. Surface water is dependent on rainfall. So if there's a lot of rain, we may have water. If there is no rain, we may not have water. So we have to conserve water. That's the first thing. The next one is to manage our aquifers. So since groundwater depends on rainfall, we must find a way of recharging our aquifers during the periods where we have heavy rains. So that brings to mind the policy of one village, one dam. So that policy must be tailored towards achieving 2 goals, if I may suggest. That is, you build your dams in areas where groundwater recharge can occur, and at the same time, you can also do your irrigation agriculture. We have to also protect the sources where recharge occurs. The next thing is that we have to have water quality monitoring and aquifer mapping. That will be very vital going forward because of the drastic land use changes that are happening in Ghana. For instance, you have the Galamsey, which is polluting the rivers. That eventually will translate to our groundwater systems because groundwater and surface water are connected. So in areas where surface water recharges or contributes to the replenishment of groundwater, and you pollute the surface water, then your groundwater will also be polluted. So there is no shield where you think that, oh, maybe surface water, but we just move to groundwater. No, it's not going to be like that. Maybe after some few years, you begin to see the same effects, health effects that you experience when you take surface water that are polluted. So that must be established. When I look at the Water Resources Commission website, just trying to figure out what is happening and then write some of these policy recommendations, I realized groundwater is not being, the attention is not being paid to it. From what I see from the website, the last report on groundwater dates back to 2011. There are several reports dating to 2021 on surface water, but for groundwater, the last report on that website is 2011, which is it's something that we have to look at. We have to enforce integrated water resources management, taking into consideration the variations also that we see in the water isotope in the various regions. So, and the final but not the least, I would suggest that Ghana look at establishing what we call the Water Security Agency and model it after what we have in Canada and what we have in the US and various European countries. So water is seen as a security issue. Water is not just seen as one of those issues, because without water, we cannot do anything. Everything will come to a halt. So it's important to establish a water security agency to coordinate the activities of both practitioners and researchers. So you have an institution like that where you stock it with researchers and then also people who do the practice, community water and sanitation, water resources, a commission, putting those institutions together, bringing the scientific institutions in line and kind of harmonize that activity so that whatever is coming out of research can be directly channeled into all the various aspects of our planning. On that note, I want to acknowledge my collaborators, particularly Mr. Richie Della and Dr. Bansa Samuel. And I say thank you for listening.
Thank you very much, Dr. Bam, for that insightful presentation. Now we have about 20 minutes. We have about 20 minutes to discuss the presentation. So the floor is open. If you raise your hand, I'll give you the permission to ask your questions. But before I allow others to ask, I will want to know from you, when you were starting, you built your argument of climate variability on the fact that there is evidence of flooding in several parts of Ghana, especially Greater Accra region. The argument is, why is it in Greater Accra region and not other parts of Ghana? Don't you think it's as a result of poor urban planning and high population growth or population intensity that is really driving it rather than the climate variability? Because if the climate is really varied, then it is varying across the country. So how come the impact is centered on a smaller area rather than across the country? This is not based on a geographical way of thinking or a scientific way of thinking, but just based on intuition. Then the next question is, I wish some of my audience are not purely within the hydrology space. So I was expecting to have a basic definition of isotopes so that my people could really appreciate the context very well. That is not also to or say that your presentation was not well received. To be frank with you, it has been well received. But then I was expecting a basic description of isotopes so that those within the energy space that are trying to appreciate hydrology would also be able to appreciate it better. So these are two quick ones that you may want to respond to. Then I'll give the rest the chance to come. Thank you.
Thank you. So on the first one, why Accra and not other parts of the country? So basically, the two videos that you have here, one is from Accra, the other one is from the upper East region. So it's just not Accra, but talking about climate variabilities, what we know is the fact that you are having, say, if your rain, you used to have 6 months of rain, you may probably be having maybe 5 months of rain, or even some of the projections getting to the end of the decades is projecting about 10 months of rain, 10 months of drought in some parts of West Africa. Now, climate change, climate variability, climate has been changing since, the inception of mankind. If not because of climate change, we cannot even be living here in Canada, because if you look at the history of land formation, these are all glacial lands, and climate change has brought us actually lands that we can build on and all that. What the climate people are saying, and what we see from the record, is that you are having, instead of you to have 6 months of rain, you have 4 months of rain or 3 months of rain. And when it rains, the intensity of the rain, the amount of rainfall that happens is far more than, say, a rain that you should have about 1 week to have that millimeter of rain may occur maybe within just 24 hours. So the intensity is high. So that's what the climate variability is about. It's about you, if you used to have, let's say, 15 or 20 millimeters of rain in Accra on a daily basis, now you may have about 50 millimeters of rain, and that is the issue. And if that is, if that rain, 15 millimeters of rain are supposed to occur for a week, is occurring in a day, so that becomes an issue. So in some areas you will have a lot of rain, and in some areas you have drought. What this whole thing, when I look at climate change and what is happening, is just like the dream that Pharaoh had, where you have years of abundance and then years of scarcity. And it doesn't mean that energy is not balanced or mass is not conserved. That's not the case. So that is what is happening. Now you say Accra, of course, if you don't plan well, that is what we are talking about this thing, so that we know what to do. So if you used to have 20 millimeters of rain in Accra for a period of 1 week, and you are having that 20 millimeter of rain in Accra within just a day, 24 hours, and you have poor planning, you have not designed your infrastructure to take care of that, definitely you will have floods. So the idea is to prepare. And to prepare and to construct, we have to understand how the system will be like as we move forward. The other one, you talk about isotopes. So isotopes are basically atoms of the same element. So we take water. So if you take water, everybody know water is H2O. So water is made up of hydrogen atoms and then oxygen atoms. Now, when you take oxygen as an element, you have variation in the amount of proton and neutron that you find in the nucleus. So that difference, so oxygen has, say, 3 isotopes. Oxygen 16, 17, and 18. Hydrogen have 3 isotopes, hydrogen 1, hydrogen 2, and hydrogen 3. So in your water molecule, you have all these isotopes in there. And what basically we do, because this can be measured, we measure the stable ones in this particular presentation. We just rely on the stable one, which is oxygen 18, for instance, and then deuterium vis-a-vis deuterium 1, and then oxygen 18 vis-a-vis oxygen 16. And then we see how much of these isotopes are in the water molecule. When you put a pan of water on fire, you will see that the water will be evaporating, but all the water doesn't leave the pan immediately. It's because of the differences that you have in the mass of the various oxygen and deuterium that form the isotope. I mean, the water molecule. I don't know if that answers your question.
Would open the floor. At the peak during the presentation, at the peak, we had about 67 people present or joining in. Thank you very much for attending. So EFO, that's the name I'm seeing. FO, EFO, FO. Your hand is up. So please unmute and go ahead with your question.
Yeah, hello?
Yes, we can hear you.
Okay, first of all, good afternoon to you guys in Ghana, and thank you for this opportunity. Bam, thanks for this presentation. It's been very enlightening. I have 2 questions for you, and I don't know if that's your space or if you've considered it, but the key takeaway that I got was, one, the drought, or the if you have a lot of rain, and the second one I got was the galamsey issue, which you didn't really go much into detail. But my first question to you is, do we have an elemental composition that has been done on the river bodies in Ghana? Because I did see that you did show the weather pattern of Ghana, but has there been an elemental composition that has been done? And the reason I ask is because looking at the recent event that has been going on in Ghana in terms of pollution of the water, right? And considering the fact that fishery is one of the big agricultural, employment for our villages, right? What is the impact, economic impact and health impact that you project? It's something that we will likely Ghana will face in the future. I ask this because if I look at the recent galamsey issue, there's high mercury. In my prediction, there will be high mercury elements in some of the fisheries, which is known to have birth defects, right? I know this might not be your field, but what do you think would be the correlation? And also, do you plan to do an elemental mapping of the Ghana water bodies that will correlate to the health or economic impact or thereof for Ghana? I hope it's not too much.
Oh, not too much, Chris. I think a lot of people are working on hydrochemistry, hydrogeochemical studies in Ghana, and people have been looking at water quality and the changes that are happening in the rivers, both groundwater rivers and then also groundwater. So, I mean, this particular presentation is just about how we can tell the relationship between rainfall, groundwater, and then surface water, and what that will mean in terms of planning. Now, from what we get from this is that some of the surface waters or the surface water groundwater connection in our system. So where groundwater, in areas where groundwater is fed or replenished by surface water, what is happening to those surface waters in terms of pollution via galamsey will eventually end up being recorded in the groundwaters. I mean, take the case of Alberta, where I do some of the works in the oil sands. So you will see that the mining activities that have been going on in the area has been reflecting in some of the groundwater systems. Yeah, and so I expect that some of those will be reported. I think there was a study in the Western region sometime about groundwater and groundwater quality, and then there were some reports that indicates that what was happening as far as galamsey and the use of chemicals that you mentioned were concerned, that was being noticed or measured in some of the groundwaters. Trace metals like mercury, arsenic, and things like that were being measured. So the point is, sometimes it may appear that, oh, what's happening on the surface, say our surface water bodies are being polluted, and we are fighting Galamsey people to stop, and we are thinking that probably will be the end. That doesn't seem to be the end. We did some work in the upper east region, and that place we measured nitrate and tritium together with the oxygen 80 and deuterium. What we saw basically, and I think my colleague Abbas also did some work there, and it's clear that you have some of the nitrates that are being used either from chemical fertilizers or say animal dung. You are having some of those nitrate signals in the water, even chloride, from what do you call it? Give the chloride that they give to those animals. Some of those signals will be seen in the groundwater. So what's happening on the surface will eventually happen. Particularly, you have rainfall. You are seeing a signature that is telling you that your rainfall is the same as your groundwater. And you know that the rainfall has to go through the soil to replenish your groundwater. So that is that. And for the flood and the drought, particularly the rivers, that is very clear that some of those rivers that we have studied, if you have these flood situations happening, so it means that all those communities that are around those rivers, if you are doing construction, you don't take into consideration these kind of observations. And you just build a bridge because it's dry season, just build a small bridge. When it's rainy season, to be washed away. Yeah, and we can build structures also to conserve the water in the rivers so that they can withstand the drought. And so those are some of the things that we can do. Yeah, thank you.
Okay, thank you very much. So I'll be taking my last round of questions since my time is almost up. I can see Abdul Raf, your Dr. Raf, you have the floor. Raf, please, you have the floor. Unmute and go ahead with your question. Yes. You unmuted, but you've muted again.
Okay, thank you, Prof. Can you hear me now?
Yes.
Yes, and thank you so much, Dr. Bam, for the insightful presentation. My point is on the policy recommendations, especially the groundwater management, the point 2. I've not heard anything about, you've not highlighted the wetland as a strategy for aquifer recharge or management of groundwater. And I think that wetland management or restoration would be a cheaper and more economical compared to building dams and dugouts. Though the dams and dugouts also have their specific aim apart from aquifer recharge. But I think that wetland restoration, especially like flood plains of river bodies, will give us more impact when it comes to aquifer recharge. I don't know whether you share that view or what do you have to say about that?
Yeah, I mentioned a one village, one dam because it's a policy of the government that they are pursuing, right? So yeah. It's just to fine-tune that policy to serve two purposes. That's why I mentioned that. On the issue of wetlands, so I did my PhD on prairie wetlands and what the connection is between those wetlands and the groundwater. Wetlands in general so you have different types of wetlands and they serve different hydrological purposes. Some are recharge wetlands, some are discharge wetlands, some are flow-through wetlands. So, and even those ones that might seem to be recharge wetlands, they have to be studied to actually ascertain that they are recharge wetlands and they can contribute significant amount of recharge to groundwater. So those wetlands that we have in Ghana has to be first off studied. We have to study them and see whether these wetlands are not groundwater discharge, points. By just salinity and all of that, you can tell. And few isotope studies and some measurements like that. So you have to study that first. You have to first off study that. So the same thing with the one dam, one district. If you want it to serve two purposes, you first off have to understand where you should be siting that dam for it to serve the two purposes that I'm talking about, recharging and at the same time, you using it for irrigation. So the wetlands will be good, but you have to first off study them and know whether this wetland is a recharge wetland, a discharge wetland, a flow-through wetland, before you can come out with that conclusion. In our case here in Saskatchewan, those things that I mentioned, recharge, discharge, we have that. So initially the understanding is that wetlands recharge groundwater. But when we measure the total composition of all the wetlands and match it against the groundwater, we realize that there were vast difference, and we categorize the wetlands and then relook at the isotopy composition. That's when we now realize that ephemeral wetlands, ephemeral ponds in the wetlands were the ones contribute most to recharge, rather than the big wetlands that you see a lot of water in them that last years and years. They don't seem even to contribute anything, rather they were recharging groundwater. They were rather receiving groundwater discharge. So that's the thing you have to look at. So it cannot be a blank check like we just have to restore. I agree we have to restore wetlands for other functions, ecosystem services. However, if you want to use them for the purpose of groundwater recharge, or you want to restore them because you want them to recharge groundwater, then you have to study them to be able to come out with that this wetland will contribute to groundwater recharge. This one may not.
Okay, thank you.
You're welcome.
Thank you very much. On this note, we want to bring today's session to a close. We've gone past our time by about 3-4 minutes, but please spare me an additional minute to acknowledge the following. So we had our registrar joining us, the Vice Chancellor as well joining us. We had Professor Mike Champon also joining us. We had Philip Asio Doji, if I got your name right, also joining us, and FO also joining us. The rest are all faculty members of the university, and we are really grateful for your time. Once again, Dr. Edward Abam, we want to sincerely thank you for sacrificing your time. I know it's very early where you are. To wake up at 5 a.m. to get ready for such a presentation is something that we really cherish and appreciate. On this note, we want to say thank you very much, and we hope to see you once again another time. This is an announcement. Our next session will be on the 31st of May, where we invite another person of a top-class scholar to also share with us on an insightful topic. On this note, I want to say thank you to all of you. Thank you, my colleagues, for joining me, and may God richly bless us all. Bye-bye.